So here's an example that we're given of the circuit that has a 10-volt power supply, and in the statement of the question, they're asking us to find the equivalent Norton circuit that would supply the same current to the resistor RL. So here is RL right here. And so what that means in a sense then is RL is not a part of what we're calculating the Norton circuit for. So that means this would be the terminals for the circuit that we're interested in. So we need to find the Norton equivalent across those terminals. So let's look at how we would do that. So the first thing is just remembering that this is where our terminals are. So RL, like we said, is not a part of the circuit. That's the load on the circuit. So that being the case, we can remove it for now, and we're left with this circuit. And so the first thing that we would want to calculate then is this input resistance, looking back into here. Some might call that the Thevenin resistance, so RTH, either one is fine. And when we do that, remember that we short out all voltage supplies and open circuit all current supplies. So we only have a voltage supply here, so we will short circuit this, or replace it with a short circuit. And so this is what we're left with. So now a quick examination, we should see that this 4 ohm and 5 ohm are in series, and likewise this 2 ohm and this 3 ohm are in series. So we could just combine those into one. You just add them. And so if we were to do that, let's just do that real quick. So it'd be as if this one's not here at all. I'll change the value of that to 9. And then likewise, it would be as if this one were not here. I'll change this value. So these are shorts, and this is a 5. So here's our equivalent circuit now. So now, by inspection again, we should be able to see that we have this 9 and 6 are in parallel, and likewise this 5 and 1 are in parallel, and then those two are in series. So what that's going to mean then is that our R input, or R Thevenin, is going to be equal to 6 in parallel with 9 plus 5 in parallel with 1. And so when we calculate that out, it'll be, well, we can write it out. It's 6 times 9 over 6 plus 9 plus 5 times 1 over 5 plus 1. And so that's going to equal to 54 over 15 plus 5 over 6. And so that comes out to be about 4.43 ohms. So that's our resistance that we would use for the Norton equivalent. So now we need to come back here and reset our circuit. And now we need to find out what our short circuit, and remember, if we have this terminal here and this terminal here, we want to know what the short circuit value is here. So in other words, if we were to come back and put a short circuit here, what would be the current that flows here? I short circuit. And so looking at that in a sense just means, again, RL is not here because it's shorted out this time. And so now we want to determine what that current would be. And so the best way to do that would be by loop analysis or mesh analysis. So that being the case, we're going to define some mesh currents here. So we'll call this one, I3. We'll call this one I2. And finally this one we'll call I1. So now we can go back and write our voltage loop equations. So let's do that. So we'll start with the I1, which is in the green. And when we do that, we see that we have a 10-volt supply. So we'll put that on one side, and that's got to equal to the voltage drop of all the other resistors. And so when we start to do that, we see that we have this 4 ohm resistor. So that's going to be 4 times I1. And we see that we next we'll have this 6 ohm resistor. And so that one will be plus 6I1. But then we also have this I3 working against us. So it's going to be minus 6I3. And then finally, we have this resistor here. And so that's going to be plus 5I1. So that's the full loop for the I1 mesh current. So now we can come back and do the second I2 mesh. And so when we do that, there's no voltage sources. So then we'll put a 0 here. And then we just need to do sum up the voltages around the loop. So we don't have any contribution from I1. But let's go through the resistors. So as we go through this, we'll start with this 2 ohm resistor. And so that'll be 2 times I2. And then we'll have this 3 ohm resistor. And so that's going to be 3, let me write that a little neater, plus 3 times I2. And then finally, we will have this 1 ohm resistor. And so that'll be plus 1 times I2. But then we also have this I3. It's going to be coming back around the loop that way. So it'll be minus 1 I3. And again, that's all equal to 0, and that's all the components there. So finally, we can do the one for the I3 mesh current, which the I3, incidentally, will be our short circuit current because that's what flows through that short across the terminals. So as we look at that one, again, we see there's no voltage sources, so we can set a 0 on that side. So I just need to sum up the voltages on the other side. So we already see in blue, we have the 6 ohms, so that'll be 6 times I3. But again, we have this current from I1 working against us, so that'll be minus 6I1. And then we have the 1 ohm resistor in purple, so that'll be plus 1I3. But again, we have I2 working against us here, so that's minus 1I2. And that should be everything. So now we can rewrite these equations by combining like terms and simplifying this a little bit. So this first equation, this will end up being 15I1 minus 6I3, and that'll be equal to 10. This next equation is going to be 6I2 minus I3, and that's going to be equal to 0. And then finally, we'll have from this equation minus 6I1 minus I2 plus 7I3, and that's also equal to 0. So here we have 3 equations, 3 unknowns, and you can solve these in a number of different ways. You can put this in matrix form. You can use term elimination, several different ways. But the bottom line is 3 equations, 3 unknowns. We should be able to solve for all of these. And when we do, the one we're interested in is I3, because that is equal to our ISC short circuit up here. And we come up with 0.9 amps when we solve for that. So now we have our input or Thevenin resistance. We have our short circuit current. This is all we need to construct our Norton equivalent. So when we do a Norton equivalent, we recall that we have a current source, and that's our I short circuit. So that'll be 0.9 amps. And then that will be in parallel with the resistor, which is our Thevenin resistance or input resistance. And so that's 4.43 ohms. And so this is our Norton equivalent circuit, that when you put that in place of those terminals, and if you were to put that RL resistor across there, it should behave exactly the same.